Good morning, everyone. This is Jackie from Apoya University. I'm the lead for this project, development of theoretical and computational models based on percolation theory, leading towards durable material design. This project is being implemented together with my collaborators from Japan and from Apoya University. There are three rationales for pursuing this project. The first is the curiosity. We'd like to reproduce the stochastic, spatial, and temporal characteristics of electric discharge and optical breakdown in materials. We would also develop skills among our students to computational modeling and seek applications to material design and other optical phenomena. Throughout the course of this project, we would like to foster interest in research and development and increase scientific activities among our collaborators. So why percolation theory? It's a statistical tool for observing complex behavior, such as a phase transition, or a stochastic process based on the formation of clusters, which can lead to the formation of defects, membranes, or defining interfaces. Here is an example of a percolation model in two-dimensional square lattice. So each square represents a site, and each site is given a probability P. The system will percolate, forming clusters depending on the probability of each site. For example, here, the yellow dots corresponds to a cluster with 7 elements. So it's a cluster of size 7. The red dots correspond to another cluster, and it has a size of 3. And also there are 2 clusters with a size of 1. So percolation theory computes the characteristics and the evolution of these clusters. So we are interested in using this model because number one, it is scale-free. We can treat a cluster on a microscopic level and apply the general behavior of a system to a macroscopic system. The cluster formation is defined by a probability threshold. Although it's not exact, we can use numerical calculations to reproduce systematically this threshold. There are 3 objectives for this project. The first is to develop a theoretical and numerical framework for the process of electrical discharge and optical breakdown. The initiation and propagation of breakdown in materials due to a strong electric field is inherently stochastic and also complex. This has yet to be fully explained, thereby a percolation model from our system may be a good starting point to replicate the results. We formulate our model based on the insulator to conductor transition in 1D and 2-dimensional electric circuits. So we start with the 1-dimensional model of electric discharge, where we have a column of air, such as that from the ground towards an altitude to the electrosphere, and we investigate the formation of lightning in the thundercloud. So through this 1-dimensional air column, we reproduce electric discharge and its characteristics. We'd like to understand the physics of breakdown, how it happens and when it happens. We investigate the criticality and characteristics of this discharge as we build skills in numerical model and programming. We use an electric circuit of resistor network as the cell components for percolation. So this initial model showed us that the charging mechanisms and the initiation of discharge is quite a complex process. However, thundercloud models are points of interest, especially for climate monitoring and predictions. The probability of breakdown and electric field calculations at each cell is very necessary to find patterns in the process of the discharge. Currently, we are validating our numerical results against physical measurements. Eventually, we extend our model to a 2-dimensional system to recreate and reproduce discharge or optical damage due to the strong laser field irradiation in an optical material. We consider laser-induced optical damage as a microdischarge in this model, but we apply our electric circuit model using appropriate boundary condition per material. The laser interaction and solid-state physics will be investigated to reproduce the experimental damage threshold. This prediction will depend on the material properties. So why ALD? Well, it is a huge concern in high-power laser systems. Recently, by focusing 192 beams onto a target, compressing the hydrogen target hydrogen is able to generate 1.3 million joules of energy. This process via laser fusion is deemed a promising source of renewable and sustainable energy. However, the formation of damage in materials will limit the performance of these laser systems. It can affect laser crystals, nonlinear crystals that were used for down conversion of the laser to appropriate frequencies, the windows and surfaces of mirrors that are used in such facilities. So ultimately, our goal is to be able to develop a model that will allow us to predict the material performance at these levels. Thank you for the support.